Z-score is a really important measure of position. It's going to come back a real lot second half of the year. It's going to become increasingly important. So let's give an example. We have air trapped in polar ice sheets at particular depths can give us information about the planetary atmosphere at various times in the past. Many measurements taken at a particular depth reveal that the average concentration of carbon dioxide at that time in history was 235 parts per million with a standard deviation of 46. The question now is, if an ice core sample is tested, and it's from a particular depth, the same depth, if this sample is tested and returns a measure of 106, what is that measurement's z-score? Well, to figure out what z-score is, we go back to our number line that we made before. Right? Remember our typical, unusual, rare outlier zones. And what did we do? We went 1 standard deviation, 2 standard deviations, and 3 standard deviations, both above and below. And we got these numbers. Well, z-score is, in fact, just the number of standard deviations away. So if we look at 106, oh, that's somewhere here in the rare zone, right, which is how we answered that question before about the yak cheese. So z-score is going to be negative 2 point something. It's between -2 and -3. It's just, z-score is just a numeric way of getting after that rare idea. So what we do is we find the distance from the mean, right? That distance, right? We divide by our standard deviation, and that gives us the number of standard deviations away from the mean. So there are the numbers. It's always data minus mean. Right? So there's our distance, standard deviation, and it's 2.8. Actually, we'll do that. Negative 2.8, which if we look back at our number line, makes sense. Negative 2.8 seems to coincide with what we'd expect. And that tells us that it's a rare measurement, and the negative tells us that it's below the mean. So it's rare and small. Now, next question is essentially going backwards. If we have the z-score of 1.75, what would be the actual data measurement? So 1.5, of course, positive would be to the right. It'll be between 1 and 2 standard deviations, so it'll be somewhere around here. So it'll be between 281 and 327, the actual data measurement. We have to figure out what that is. Well, we can take how we calculate z-score, and we can make it into a formula. We have distance from the mean, right? And here's the more formulaic way of doing it. Data measurement minus mean, divided by standard deviation. That's our z-score. Now this is one way you would see this equation. There is another way that you can see it. If we just rearrange, if we multiply both sides by standard deviation, right, it comes over here. We're just doing algebra here, right? If we then, add x bar or the mean to both sides, right, we've gotten our data measurement by itself, which is really what we were asked for. And we have our equation for the data measurement. Notice that these two equations are really just forms of each other, so they really are interchangeable. You can use either one. We could have actually stuck with this one and just solved for this, plugged in the numbers for all the other pieces. It's sometimes convenient to have this already pre-solved for you. You plug in the numbers, and you get your data measurement of 315. Right? And you come back, and is that between 281 and 327? It is. It kind of makes sense. Have high confidence. And that's the answer to the question.